Morning, everybody. What an event. This has been an excellent discussion all week, and I've really appreciated the opportunity to be here. I come from a family of engineers. My brother works in nuclear engineering at Duke Energy, and my dad spent his career drilling natural gas storage wells in western Pennsylvania and West Virginia. I grew up with drill bits and geodes decorating our house, but when time came for me to go to college, I decided to rebel, and I went to study pharmacy. It didn't take long for me to realize that I'm an engineer at heart, so I quickly switched to chemical engineering, and I have spent the majority of my career in my 18 years at EPRI focused on emerging technology and supporting implementation of new tech. So this summer seminar has been about first movers and shrinking technology gaps. There is a big gap to close in commercialization of super hot rock geothermal technology. So that's what we're here today to talk about. For background, there is a massive amount of energy in the Earth's core accessible within 20 kilometers of the Earth's surface. It represents a major potential source of dispatchable, zero-carbon energy that has a small above-ground footprint and minimal environmental impacts. Enhanced geothermal technologies, and super hot rock specifically, represent the potential to have 10x the power production over conventional geothermal wells, and the technology can be applied in many, many more locations. Almost everywhere you can find within 20 kilometers of the surface, super hot rock energy resource. If we think about conventional geothermal technology, it's pretty simple, really. It's a connection of injection and production wells that use to flow a working fluid through a thermal reservoir to gather heat, make steam, and to make power above ground in a steam turbine. It's limited today to places where the heat is very near the surface. There are 16 gigawatts of commercially operating geothermal projects around the world today. Most of those have their depths at about 2 kilometers where they access their heat. The average production per well of those plants is about 7 megawatts of energy. When we think about enhanced geothermal and super hot rock specifically, we're thinking about much deeper rock formations with much higher temperatures than what we're accessing today. The depths that we're thinking about are not 2 kilometers, they're between 5 and 20 kilometers deep. The temperatures that we're looking for downhole are at about 450 degrees C, where the rock is, kind of molten. That energy represents an opportunity to create much higher quality steam. So as we're thinking about the commercial opportunity for enhanced geothermal and super hot rock, there are 3 key factors that we need to consider: the depth of thermal reservoir engineering and reliable design for the power equipment. It is today not economical to reach the depths required with current drilling technologies due to the hardness of rock and the temperatures that we observe at the depths that we're looking for. There has been significant investment in advancing drilling technologies, and there are many mechanical and non-contact drilling options available today or becoming commercially available as we speak. One example is millimeter wave drilling. Think of it like a high-intensity laser that can be used to cut channels through rock, in order to enable the access to the depths or to enable fluid flow through the reservoir. It's like a combination of Superman's heat vision and some Bond villain technology to rob a bank. And there has been testing underway in labs over the last couple of decades, and we're getting to the point where that is nearly commercially available. If we get to the point where we do have those breakthroughs and economical high-intensity drilling is available, that will be a breakthrough for super hot rock. The next thing is the thermal reservoir engineering. At the depths that we're talking about, the reservoirs are pretty impermeable in most cases. We need to create channels for the fluid to flow through the reservoir to gather that heat. And so a lot of the focus here is on hydraulic fracturing or other engineering techniques to create those fluid channels for the working fluid to move and gather up that energy. Some companies are even thinking about closed loop systems to connect the injection and production wells. The third is reliable design. The mineral composition in the reservoirs that we're looking at create a lot of challenges for the chemistry, especially for the above ground equipment. The systems will be operating at much higher pressure and temperature. So we're going to need materials, cements, and casings that can withstand the harsh environment for reliable well development and operation. We also need advances in power cabling and other instrumentation technologies that can operate at the depths that we're talking about, and especially at the temperatures that we're talking about. There has been a huge amount of effort to date, funded by the oil and gas industry, by the Department of Energy, and governments around the world. We're at a point now where technology innovation is meeting market opportunity. We see decarbonization objectives accelerating as we go, but the absolute requirement to maintain system reliability and resilience is still there behind us. We have to meet these goals. Through first movers like Southern California Edison, who recently signed a power purchase agreement with Fervo Energy for 350 megawatts of geothermal technology, we're starting to see market signals combine with the technology development. As we look forward, we see super hot rock geothermal potentially being available within the next decade. My dad was a first mover in a sense. He spent his career in geology and working on drilling. His work predated, though, the natural gas boom, the broad deployment of wind and solar technology, and all the advances we have seen in hydraulic fracturing, drilling, and other geological engineering that now make super hot rock geothermal technologies possible. The challenge for us as the next generation of first movers is how to apply the lessons of the past to achieving our goals going forward. So in the words of this meeting, I would say, let's go super hot rock geothermal. Thank you.